Alright, hi year 11s, this is our last video on chemical bonding on allotropes of carbon, so let's get started. So we learned about covalent network structures, and so we're going to talk about some of the allotropes of carbon that are these covalent network substances and how their different arrangements affect their properties. Okay, so allotropes of carbon, so carbon is in group 14, and as we said, group 14 is capable of forming covalent networks generally well because they have four different a bonding capacity of 4, which means it can form 4 single bonds, which means it can do lots of cool stuff. They can form different arrangements of covalent networks under different conditions. All right, and these different arrangements of carbon covalent networks are called allotropes of carbon. Okay, those are the different arrangements. So each allotrope of carbon has different properties. All right, and so therefore these properties of these allotropes have led to different concepts of arrangements, and so therefore that's how we kind of worked out what they're kind of structured like. So let's have a look. Diamond being the most common one. Okay, so it is brittle. It is very high melting boiling point, and again, diamonds don't really melt, they decompose, and they're non-conductive of electricity. These are its properties in solid, in both solid and molten forms. So these are its properties. Okay, and what they think that diamonds are is that it's a network of carbon atoms where each carbon atom is bonded to 4 others in a tetrahedral arrangement. This arrangement is very stable and very strong, making diamonds one of the hardest materials in the world. Okay, so that's probably not the best diagram that I probably could have found, but the idea is that each carbon is bonded to 4 other carbons in a tetrahedral plane. Okay, so therefore, like you think of like a little triangular pyramid. Okay, where these lines there make a little line, so it's like a little triangular prism. Okay, so a triangular prism is the structure of one tetrahedral, and then each of them is bonded to another tetrahedral structure. Okay, and it goes on and on and on, and it forms this very regular pattern here, right? And because they're all a regular pattern, all of those covalent bonds are very strong. It makes it very compact, very strong, and very hard. There's no mobile charge carriers, so they can't conduct electricity, and they've got a very brittle, because if you move any of the atoms, they're going to break, and that's not going to be great. Okay, so next is graphite. That has a very different thing. So it's slippery, again, a very high melting and boiling point, and conductive of electricity in solid form. So this is one of the unusual ones where you can conduct electricity in solid form, because all you need, keep on going. It's a network of carbon atoms where each carbon atom is bonded to 3 other carbons rather than 4 in the diamond in a hexagon shape. Many of these hexagons combine together to make a single sheet of graphite, also known as graphene, right? And then there are weak van der Waals forces between each sheet, meaning each sheet is very easy to separate from other sheets, making the substance very slippery. Okay, so effectively, if you were to apply a force across this one here, this sheet here would move because there's only weak forces between the sheets. Okay, so that entire sheet would move, but all of the atoms within that sheet would still be bonded together. So the sheet would move, not the individual atoms. All right, that's what makes them slippery. Each sheet contains strongly bonded atoms of carbon, which means separating the atoms of carbon from each other is difficult. It requires a large amount of energy, i.e. they have a very super high melting boiling point and generally will burn rather than melt, right? And then the 4th electron in the outermost energy level, because remember it's only bonded to 3 other carbons, is not bonded to anything and is delocalized and is able to move through the structure, giving graphite the ability to conduct electricity in solid form because it effectively has a mobile charge carrier, all those little electrons flowing through those sheets. Okay, cool. So let's have a look. There's a couple of other forms. You may have heard of graphene, where it's a single sheet of carbon. What's exciting about graphene is that because it's a single sheet, it's effectively going to be very, very light. But if you apply a force this way on that sheet, all of those strong covalent bonds hold together, and so therefore it's very strong in certain dimensions, right? And it depends on how you attach them together, and if you were to even try and pull them apart this way, that would also be quite difficult. And so therefore, single layers of carbon called graphene are very strong for their weight. All right. Also, we have carbon nanotubes. So imagine if you take a sheet and then you roll it up into a circle, all right? And that's what a carbon nanotube is, all right? These carbon nanotubes, again, will be very hard to pull apart in these dimensions, all right? And generally, they're also hard to squish in that dimension as well. And so they can provide a lot of cool stuff when they're all packed together, or when you've got a whole bunch of these carbon nanotubes holding stuff. They have a very high tensile strength. All right, so let's go over to the next one. Buckminster fullerenes. Okay, so Buckminster fullerenes are slippery with very high melting boiling points, and they are non-conductive of electricity. So they are networks of carbon atoms where each carbon is bonded to 3 others carbons, and they form hollow spheres of varying sizes. So you can get small Buckminster fullerenes or even large fullerenes. Okay, so there are weak van der Waals forces between each fullerene, meaning that they are able to move over one another, making them slippery. Okay, this means that they can be used as a lubricant in situations where water oil is undesirable. Okay, so if you have a look at the structure here, it's literally of a ball. And if you have a whole bunch of these balls over 2 surfaces that are between them, they can roll around. Okay, and then if they roll around, then they can allow the 2 surfaces to move in opposite directions. And not cause any or too much friction, especially when you don't want water and oil to be there. Okay, so it's effectively known as a dry lubricant. Okay, so that's their ability to be slippery. The 4th electron, again, in the outermost energy level is not bonded and is delocalized, which would make you think that they could conduct electricity. However, it is localized to each fullerene or each ball. So that means the electrons can flow through one ball, okay, and move around in that ball, but it can't move to the next ball, okay? So it can't move to the next ball, and therefore it can't conduct electricity because these balls are quite small. They're like at the atom level, so therefore, trying to get something from one side to another is actually going through multiple of these fullerenes, and therefore you're not going to have that electrons jumping from ball to ball. All right, so they have a delocalized electron, but they're localized within each ball, all right, and therefore they can't conduct electricity, okay, which is also useful when you're being a dry lubricant with metals as well. Then finally, we have amorphous carbon, which is brittle, high melting boiling point, and non-conductive of electricity, and this is generally the carbon that is coal or soot, and it's just kind of a randomly jumble of atoms, okay? They're not forming a nice, pretty structure, and so therefore in a non-uniform manner. Okay, the lack of uniform matter makes that they are quite weak as well as brittle. So instead of it being hard and brittle like diamond, this amorphous carbon is weak and brittle. Okay, because there's no uniform structure. If you were to push a certain portion of it, okay, it would just break along some sort of plane because all of the bonds are there, but they're not very organized. All right, it's because they have no consistent delocalized electrons, they don't conduct electricity, okay, because most of those electrons are taken up in bonds or just floating around waiting to take up another bond, so they're not really delocalized in a coherent manner. Okay, so these are the 4 allotropes of carbon that you need to kind of know about: amorphous carbon, Buckminster fullerene, graphite and its derivatives, and diamond, and they all have different types of properties based on their structure. So you need to kind of know their structure and be able to talk about them, each of them, in detail. All right, so go have a read of all the notes again, or watch this video again, get my views up, and then you'll be fine. All right, and that's it for chemical bonding. Woo!